All right, so in this video lecture, we are going to talk about the derivatives of trigonometric functions. And in order to start that off, we're just going to dive right into an example. So in example 1, it says, given f of x equals sine of x, estimate f prime of 0, f prime of pi over 2, f prime of pi, f prime of 3 pi over 2, and f prime of 2 pi. Now I want you to remember, how do we visualize the derivative? Hopefully you said slope at the tangent line. So I have a tangent line drawn for us at 0. And remember, the way that we calculate slope is the change in y's over the change in x. So I'm going to use one of the points from our equation, and then I'm going to choose a second point. I think I'm going to go with the pi coordinate. Looks like roughly the output is maybe about 3.1 minus the output at 0, 0. And then our x values of pi minus 0. So I'm getting 3.1 divided by pi. 3.1 divided by pi is, I have that in my calculator as 0.8. I know I don't have the calculator pulled up, but you can verify it. Or I'm sorry, 0.98, which is roughly 1. Keeping in mind that I estimated the output of 3.1 at pi, I'm going to go with 1 as more approximately whatever my slope value is at 0. So I would like you to go ahead and do the same slopes for pi over 2, pi, 3 pi over 2, and 2 pi. And I will have my work up on the board as you go. Horizontal tangent, so slope of 0. I don't want my graph to look too cluttered though, so I'm going to get rid of that. Backwards order of f prime of 0, so this should be approximately -1. That looks like it's about the same calculation as what we had at 0. So I'm going to say that that's going to be approximately +1. So if we go ahead and look at all of the outputs here for these slope values, 1, 0, -1, 0, 1. It looks like, in general, our derivative of sine is actually cosine. And you know what? I'm going to check that out in my calculator. Math 8. We're going to take the derivative of sine of x, and we're going to leave it as x there. And then I think that my derivative is the cosine function. I'm also going to double check that I am in radian mode, which I am, so that's good. So we're the calculator is plotting what it thinks that the derivative is, and it just plotted what I think the derivative is. We're getting the same graph. So cool. The derivative of sine is cosine. I would like you to go ahead and for example 2, do the same exact thing that we did in example 1. I'm going to have my answers appear in 3, 2, 1. Okay. So it looks like we are getting the values 0, -1, 0, 1, 0. But those values are the opposite of what the sine function are. Sine, if we look at the graph, goes from 0 to +1, 0, -1, +1. So it looks like we kind of have the reflection of the sine graph over the x-axis. So I think that the derivative function of cosine is negative sine of x. And I'm going to check that out in my calculator. All right, so first graph is going to be what the calculator says the derivative function is. The second graph is what I think it is. Fingers crossed. Yay. Okay, so the derivative of cosine is negative sine. Next example is the derivative of tangent. Now we're not going to do it the same way as sine and cosine. So we're not going to investigate derivative values at those points. But instead, I would like to actually use quotient rule now that we know what the derivative of sine and cosine is. So first things first, if I want to be able to use quotient rule here, I better rewrite tangent as sine and cosine. And I'm keeping the derivative operator, the d dx, because I haven't taken the derivative yet. I'm just rewriting tangent. Now, since I'm going to do the derivative next, I get to drop the operator. So we have low, d high. Now, if you want to write d high as derivative of sine x, go for it. Or we can just go straight into the derivative. I'll leave it like this for now, but personally, I don't like writing this notation. I like to just go straight into the derivative. It's just my preference. So we have low d high minus high d low. Over the square root of what's below. All right, now I'm actually going to write in what the derivatives are of sine and cosine. Derivative of sine is cosine. And then the derivative of cosine is a negative sine. Pretty this up a little bit. Cosine times cosine is cosine squared. And then negative sine times negative sine is going to be plus sine squared. All over cosine squared. Now in the numerator, there is a trig identity that I hope that you recognize. There are not too many that I hope that you have memorized. This is one that I do hope that you have memorized. So I want you to take a look on your green or whatever color it's printed out this year, your green trig identities page, and see which trigonometric identity we have in the numerator. Now, if you ever lose that paper, you could just Google trigonometric identities. And I honestly just like to look at the images because there's usually really nice like printout style versions of these things versus scouring through a website. But if you look at the Pythagorean identities in the middle, sine squared plus cosine squared equals 1. Here we have cosine squared plus sine squared. So that must equal 1 over cosine squared. One over cosine is secant. So 1 over cosine squared is secant squared. All right, let's fill out our table of trigonometric derivatives. You know 3 of them. I'm going to tell you the other 3. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. So now, just like how every trig function needs its like sine goes with cosecant, cosine goes with secant, and tangent goes with cotangent, each of these pairs is also going to have a negative. So if sine's positive, cosecant is negative. If cosine is positive, the derivative of secant, or I'm sorry, if the derivative of cosine is negative, the derivative of secant is positive. And then with tangent, that's positive, so the derivative of cotangent must be negative. The derivatives of sine and cosine look similar. The derivatives of tangent and cotangent look similar. And then the derivatives of secant and cosecant look similar. This is going to seem a little bit weird, but the derivative of cosecant is cosecant cotangent, or vice versa, just negative. And if you notice, cotangent has the cosecant squared. The derivative of cosecant has cosecant and cotangent in it. Derivative of secant, take a look at the one that's similar to it. So instead of cosecant, we have secant. Instead of cotangent, we have tangent. And like I said, this one's positive. Do you notice how all of the derivatives that start with like derivative of cosecant, derivative of cosine, and derivative of cotangent all have negatives in them? All the ones that start, or that are not starting with are positive. So sine, secant, and tangent are all positives. In example 4, now that we know the trig derivatives, we can find the second derivative of f of x equals x cosine x. Go ahead and find your first derivative, keeping in mind that we have a product here, so you need to use product rule. Derivative of x is 1 times regular cosine plus plain x times the derivative of cosine. I'm going to pretty this up. Just write that as cosine x minus x sine x. If you have questions at all while you're doing this, make sure that you write them down. Taking the next derivative of cosine is just negative sine. But then when I look at the next term, I have a product. So I will have to use product rule again. I'm going to treat this as a negative x and a regular sine. So derivative of negative x is negative 1 times regular sine. Then I'm going to write down my negative x times the derivative of sine. And then clean that up a little bit. So negative sine x minus sine x minus x times cosine x. Oh, it looks like I have like terms here, so I'm going to write that as negative 2 sine x minus x times cosine x. I'm going to double check in my calculator that this actually looks correct, because there's a lot of sign errors that could happen, and even just using product rule incorrectly could happen. So because I'm doing a second derivative, the way that I make the calculator do this, I'm going to do it twofold here. So math 8x, and then I'm just going to type in my x cosine x here. But this is just the first derivative. So in the next line, I'm going to do the second derivative, or the derivative of that. So I'm going to do the derivative of my first derivative. And because I only want to compare the second derivatives, I'm going to turn this first function off. So my red graph is going to be the calculator second derivative. The green graph is going to be what I think the second derivative is. Just double checking that. Okay. Ooh, this is slow. If you don't like how slow this is going, you could always just compare the outputs in the tables. I just broke the calculator. We're going to check this in Desmos. You might enjoy how this gets checked in Desmos, but unfortunately you don't get to use Desmos on the AP exam. So that's the Desmos derivative. And then we had negative sine of x, -2 sine of x minus x cosine x. And we are getting the exact same graph. So yay, we did that correctly. Moving on to the last question, example 5. It's asking us find the tangent to the graph y equals tan sine theta, or tan theta secant theta at theta equals pi/4. So let's keep in mind the general tangent line equation, y minus f of a equals f prime of a times x minus a. So we are going to need y of pi/4. We're going to need to know y prime of theta. And we're going to need to know y prime of pi/4. Y of pi/4 is going to be tan of pi/4 times secant pi/4. So go ahead and get that value. Tan of pi/4 is 1 times secant is the reciprocal of cosine, so 2 over radical 2. You're going to need to use product rule for the derivative. Go ahead and try that. My answer will be up here in just a second. Derivative of tangent is secant squared. Times plane secant. Then plane tangent times the derivative of secant, which was secant tangent. Cleaning that up a little bit, we get secant cubed theta plus secant tangent squared theta. Evaluating that at pi/4, I'm just going to put the result of secant pi/4 in parentheses. So secant of pi/4, like we said before, is 2 square root 2. And then I'm going to cube that result, not square it. Plus secant of pi/4, again, 2 square root 2 times tangent of pi/4 is 1. Square root of 2 cubed is going to be 2 square root 2. Plus 2 square root 2. And then I might just want to write normally for this last part. So we get 4 over square root 2 plus 2 over square root 2. Or 6 over square root 2. And again, we can double check that in the calculator. Because my calculator's down, I'm just going to double check this in Desmos. Oh, it doesn't like that I don't have parentheses there. There we go. Oh, I have two equal signs. That's why. Okay. 6 divided by square root 2. Perfect. Okay, so we can just write our final equation. Y minus 2 over square root 2 equals 6 over square root 2 times x minus pi over 4. And we can even double check in the calculator that that actually looks like a tangent line at pi over 4. Okay, just making sure that that was the appropriate x value. I would agree. This definitely looks like a tangent line at pi over 4. It just barely skids past the, or it barely touched the graph at pi over 4. Also notice I didn't rationalize. I choose not to unless it's absolutely necessary. The reason that we rationalize when we're dealing with a lot of trig stuff is just because it's proper notation, but technically you have the answer here. So you don't need to simplify further just for simplifying sake. If you have any questions, make sure that you ask.